Hello. Whoa, hey. Thanks for being here. Thanks for sticking around. I am Mike Saunders, and today we are going to be talking about Buffer Overflow 101. So without any further ado, just a little bit about me. I've been in IT full-time since '98, got into security back in 2007. I've done a lot of different jobs in IT and security, and when I'm not doing IT stuff, I love fishing. As you can see here, not necessarily good at it all the time, but I always enjoy the heck out of it. Yes, sometimes, it's not the size that matters. That was too small to cook, So, Buffer Overflow 101, what was my motivation for doing this talk? Honestly, not too long ago, this is what I thought about buffer overflows. I knew that a buffer overflow was you copied too much data into a buffer in memory that overwrote some stuff and some bad stuff happened. And that's about as much as I understood. So how many here have ever used a buffer overflow exploit, like maybe in Metasploit or something like that? Okay, so we got a few people. A lot of you. How many have ever modified an existing buffer overflow exploit, maybe put in your own shell code or change a return address? Fewer hands, okay. How many have ever gone through and found a buffer overflow in some piece of software, figured out exactly what you needed to do, and actually wrote a full exploit for it? All right, so there's just a couple people. So this is the crowd we need here because like a lot of you, not that long ago, I was in this position where buffer overflows were magic. I knew what they were, I could modify them, but I had no idea how to find one. And if you've ever heard of this concept of imposter syndrome, Micah Hoffman, web breacher, talks about it. And it's this idea that you think everyone else knows everything and you only know this much. And I follow people on Twitter, so obviously they know everything. And I was seeing people tweeting about like, hey, I'm getting started with buffer overflows. Do you have any recommendations on how to get started? And I thought, wow, that's odd. There's other people that don't know about buffer overflows. Because I honestly felt like I was probably the only person left in InfoSec that didn't know them. So as I started thinking about that, I was talking to some friends, like, do you think this could be an idea for a talk? And they're like, yeah, absolutely. We should absolutely do this. So they encouraged me. And I submitted originally to DerbyCon, I got accepted, and then I submitted here to BSides Winnipeg, and I got accepted, and then I got rejected, and then I got accepted, and then I got rejected. And so, yeah, blame Ron. But fortunately, he accepted it again. So we're here. And before we can go on, we need to talk about a few assumptions. Things like, we're going to be talking about buffer overflows on a 32-bit x86 architecture. Other architectures aren't fundamentally dissimilar, but there are going to be things that may be different. So just be aware that we're dealing with 32-bit x86. We're doing the kind of buffer overflow where you're overwriting the stack and overwriting the return address and gaining execution control. There are other kinds of buffer overflows. We're not talking about those. And there are no protections in play here. Because this is a 101 level, we don't want to have to figure out how to bypass DEP or ASLR or stack canaries. So those are our assumptions. Moving forward, what is a buffer overflow? We should probably talk about what that is. This is not a buffer overflow. If any of you follow SubT on Twitter, you saw this. So I may say Buffalo overflow at some point here, but this is not a buffer overflow. This is. In a nutshell, buffer overflows occur when you have a program that allocates space in this thing called the stack, which is in memory. And it allocates that space to store some data, and then it writes more data into that buffer than it was intending to, or that it set aside space for, which overwrites adjacent memory. So if you set up a 100-byte buffer, and you write in 200 bytes, your first 100 bytes go in your buffer, the next 100 bytes overwrite something adjacent on the stack. And depending on what's in that space, the program might crash, data might get corrupted, and if there's this thing called a return address and you do things correctly, you can actually gain execution control. And we're going to walk through that whole process today. I've mentioned the stack a few times, so if you're not familiar with what the stack is, it's a data structure in memory, stores data in contiguous blocks, and it's typically used to store local information about a program, like things like function information, parameter values in these buffers for storing variables, and this thing called a return address, which we'll talk about a lot more. So the stack. This is not exactly correct. It's just a mock-up that'll work for today. So if you look at our stack here, Imagine you have a program that has a main function and a second function called init. The parent routine stack at the bottom, that's main stack. And then above that at lower memory addresses is where init's stack gets placed, its portion on the stack. So it's above it at lower memory addresses. That's because in this model, the lowest memory addresses are up at the top and the highest memory addresses are at the bottom. If you studied comp sci in school, you may be familiar with the stack being inverted. Highest memory addresses at the top, lowest memory addresses at the bottom, so it would be completely flipped. And that makes a lot of sense. The reason I use this model is because I learned, not at school, but by following some tutorials online, various reference material, and this is how it's laid out in the debugger that I use. If you use the other model where you're looking at it for the highest memory addresses at the top, that's fine too. You just need to be cognizant of which model you're using. And if you're used to using kind of more like hacking-based tutorials and you're Googling and you come across a scholarly article, you'll probably find that it's inverted and it will be bewildering for you because you're going to question everything you thought you knew until you realize that it's just inverted. That's the main thing you need to keep in mind. So we have our parent routine stack, and when the program loads into memory, it sets up space on the stack for the parent routine main and init. And it puts certain things like this return address, which we'll talk about in a bit, but it's how you get back to main. And then it pushes some other things like frame pointers and base pointers, and they're all important. We're not going to talk about them. And then we have a variable. We have a 50-byte variable called foo here. And that is our stack for this program. The other thing that we have is this thing called ESP, or the top of the stack. ESP is not on the stack. It's a CPU register that stores information about where the top of the stack is. And if you had just this, your stack is here. If you push some more data on the stack, we push another variable on, let's say we push bar, ESP gets updated to point to this new top of the stack. In a similar fashion, if we pop bar off the stack, because the stack is this last in, first out kind of model, so if you push something on the stack, you have to pop it off before you can get to other things that are below it on the stack. So we pop bar off the stack, and now ESP is pointing to this location. So you have an idea of what's happening with ESP, and you'll understand why this is important in a bit. I did mention that ESP is a register that keeps track of where the top of the stack is. It stores the address. It doesn't store contents, like it doesn't store data, it stores a memory address on the stack. And it's one of 8 general purpose registers. Historically, these registers had more defined functions and uses. In modern architectures, these can be used pretty flexibly depending on what the compiler wants to do or what the developer wants to do. I encourage you to read about what each of them does. However, the only one you need to know for what we're talking about here is ESP. There are also special purpose registers, things like, EIP, the instruction pointer. In the instruction pointer, it controls the flow of execution. The address that's in EIP is the next instruction to be executed. It doesn't store data, it doesn't store instructions, it stores memory addresses where instructions live. And if you can control what goes into EIP, then you control the flow of execution. You cannot modify EIP directly. That's not exactly true. There are certain circumstances where you can modify EIP, but most of the time it's modified by the kernel. It's the only way to modify EIP. So the stack, if you were to think about it, again, I like to think about things visually. So I have a program, a sample program here. And it's a command line program. You run the program, you give it an argument. So you've got a main function. And main calls foo. And it passes foo whatever we give it on the command line. And if you look at foo, it sets up one variable, a 12-byte character, C. And then it copies whatever it got in from the command line using strcpy, so it's not doing any bounds checking. It's not checking to see if whatever we gave it on the command line will fit in the buffer. It prints the data out to the screen, and then execution control returns back to main, and the program exits. Now, you don't see anything in here about like go back to main. That's because your compiler does some stuff in the background to orchestrate what happens. So when we look at our stack, we run the program, main gets pushed on the stack, init gets pushed, or what do we call it? Yeah, foo gets pushed on the stack. So we have the parent routine at the stack on the bottom. Main calls foo. So to get back to foo when foo's done running, the compiler keeps track of the memory address that called foo, or the next address after that point. It stores that address, pushes it onto the stack as the return address. So when foo gets done, the last thing it's going to do is pop that return address off the stack. That gets loaded into EIP, which tells the processor, hey, you need to go back to the code segment from main, and this is where you're going to resume execution. And we have our variable C and some other stuff on the stack. So if we run our program, demo hello, it prints out hello to the screen, and then it exits. It didn't crash. It didn't have any errors that we can tell. It seemed to exit normally. And if we looked at the stack, we begin to understand why. So we've got hello. We pushed in 5 bytes. There's actually a 6 byte there. It's a null terminator because strings in C and C++ are null terminated. So we have hello, this null terminator. Everything stayed within the bounds of our stack. So it copied that data using strcpy into the buffer. It printed out hello back to the screen, and then the return address is popped off the stack and loaded into EIP, which tells the processor go back to main, at which point the program exited just like it was supposed to. Well, what happens if we put too much data in? What happens if we cause a buffer overflow? Because we're using strcpy, it doesn't check to make sure it'll fit first. So in this case, I'm going to put 16 A's and we're going to put 4 hex CCs in. And when I put these 16 A's in and 4 hex CCs, it prints that back out to the screen, and then there's a segmentation fault. And that's an important thing to note. The buffer overflow occurs when we copy too much data into a buffer, but the crash or whatever's going to happen doesn't happen at that point. It doesn't happen until the program tries to use memory that's in that space. So we have the first 12 bytes pushed into our buffer, no problem. The next 4 bytes of A's overwrote the base pointer, and then the next 4 bytes, the hex CCs that we put in, overwrote the return address. So after, if you remember, we look at our code. Well, let's back a few more. We copied the data into the buffer. We printed it out to the screen. And then behind the scenes, there's that code to load the return address into EIP. And that, at that point, got loaded into EIP. The CPU tried to go to the address hex CC, 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 CC. And there's no data there. There's no program in that memory location. It says, I don't know what to do, and it crashes. And that, in a nutshell, is a buffer overflow. Like if you take nothing else away from this, and now you know exactly what happens when a buffer overflow occurs. It's because you overwrote this return address, and now the CPU doesn't know where to go next, and it has to crash. Now, if we do this correctly, we can actually take control of the processor and execute our own code, and that's what we're going to do. We're going to use a program called vulnserver. Vulnserver was written by a guy by the name of Stephen Bradshaw, and it's an intentionally vulnerable program designed to help you learn how to write buffer overflows. Vulnserver listens on a socket much like a web server. So if you netcat to port 80 on a web server and you type get space /foo space http /1.0 and hit enter, you have your command get, you have an argument /foo and another argument http /1.0. You hit enter, which sends a carriage return line feed, so the server now knows that delimits the end of the input by the person connecting to me, and now I need to process the data. In the same fashion, vulnserver takes a command. It's going to be trun space period. That's our command. Everything after the period is the argument to the command. We hit enter, send a carriage return line feed to the server, and it says, okay, I'm going to process that data, return something back to the screen. So what we're going to do is we're going to fuzz vulnserver. And we're not talking about fuzzing like in the sense that you're fuzzing protocols or you're fuzzing a document standard like a PDF or a zip trying to find opportunities that way. What we're doing is fuzzing the input length. So sometimes People that are like exploit developers and reverse engineers, they take exception to the term fuzzing because they think this isn't fuzzing, but there's really no other better way to describe it. We're seeing how the program responds to progressively larger and larger amounts of input. So to that end, I'm going to switch over to my VM, and if I switch into my VM and I'm doing something and you don't see it on the screen, remind me. Sometimes I forget to hit the key combo. So here we go. So I got a Python program. It's a very simple program. And we set up a counter. We have our command trun space period, and we set up an empty list, and we're going to populate that list with strings that are trun space period and some number of A's. And every time we loop through and add another item to the list, it's going to be more A's. We're going to use some simple socket code to send this to the server, and then we are going to, wow, that's weird. It's like half cut off up there, isn't it? Different resolution, never ran into this issue before. So anyways, we're going to send that to the server, and we're going to receive a response. We're going to print it back out to the screen. Very simple, and I've used this exact Python script to do find buffer overflows in multiple socket-based programs. Just got to change up the command and the data you send. So we're going to use the immunity debugger today. You can use another debugger if you want. I like immunity, so that's what I'm going to use. So over here on the left, if you've never used a debugger before, we have our code, right? So this is the disassembled code. These are instructions like push EBP, move EBP, ESP. This is the code of the program. These are these memory addresses associated with it. So when we have a return address, normally for the program, it's going to be pointing into one of these memory addresses where the program lives. That's the next instruction to execute. Over here are our registers. So we have things like EAX and ESP. We see right here, we've got ESP, we've got EIP. So this is pointing to the top of the stack down here. EIP is the next instruction that's going to execute. So now you're familiar with what the debugger looks like. I'm going to go ahead and run my Python script. And it's going to send data. You see that it sends 100 bytes, and the server says trun complete. And it keeps doing that all the way up to 1900 bytes. But when we get to 2100 bytes, I don't have a response back from the program, from Vuln server. And if we go to our debugger, you'll see that we have an access violation. It says access violation when executing 41, 41, 41, 41. There's no code over here. There's no disassembled code. If we look at what's in the registers, we see that ESP is pointing to a location that's filled with A's. ESP is not filled with A's itself. That's a memory address that it's pointing to. It's pointing to the top of the stack. And we see that EIP is 41, 41, 41, 41. So what are those 41s? Right, and ASCII capital A. So it's the hex value for ASCII capital A. So we have sent in some capital A's, and then we see that EIP is filled with capital A's. So at this point, we know we can't write directly to EIP. That happens by overwriting the return address. So I must have sent enough input in that I overwrote the return address. I know there's a buffer overflow, and I now know I can control what goes into the return address. If we look down here in the stack, we can see that it looks like we're somewhere towards the end of our input. We don't know how far. We don't have any more information at this point. All we know is that we pushed a bunch of data in the stack and we overwrote the return address and the program crashed. So to be able to figure out what to do next, we need to figure out how many bytes does it take to overwrite the return address. So key points. The program broke somewhere between 1900 and 2100 bytes, and we know we overwrote the return address with those A's. So we're going to use pattern create. Pattern create is a Metasploit utility that generates a non-repeating string of characters all the way up to about 20,000 bytes. And every time you run it, it will create the same pattern. And that'll become important in a minute. I'm going to choose 2500 bytes, so I run pattern create -L 2500. And I've already generated another Python script that has Oh, no, that's the wrong one. There we go. There we go. So I've already generated a Python script that has this. It's got our command and this non-repeating string of characters. And I'm going to send it to the server. And we see that we do not get a response back from Vuln server. And if we come in here to immunity, we see that we have access violation when executing 396F4338. It means EIP is 396F4338. There's no code there, so the program crashed. So what you would do now is you would write down that value, 396F4338, because we're going to use that in the next step, but I want to point out a couple of things to you. First, we have ESP is pointing to this location that starts with CP0C. If we go down here in the stack, we can see there's where the stack pointer is pointing to, CP0C. Immediately before that, 396F4338. That is the value that went into EIP. So that means at this point, that's where our return address lives in our input. We still don't know how many bytes that took to get there, but we know that this point is the spot where our return address lives in our input. We also know that because ESP is pointing here and the stack pointer gets updated as things get pushed on the stack and popped off the stack, we can make a reasonable guess that the program is designed to take some amount of data, somewhere between 1900 and 2100 bytes of data. It pops that data off the stack, it does something with it, and then the return address gets popped off the stack, loaded into EIP, which means the stack pointer gets updated to point to this location, which is immediately after the return address. So someone asked me before, why did I choose 2,500 bytes? Well, I chose 2,500 bytes because I know that a typical Metasploit payload, if I'm not trying to create small shellcode, is going to be between 250 to 350 bytes in length to pop calc or get a shell, do interpret or something like that. So I need to make sure there's space on the stack to store that data. Sometimes there's not, and you have to do things like egg hunter exploits, and there's other ways of doing overflows, and those are more advanced. But because this is a traditional buffer overflow 101, we want to make this as simple as possible. So we need to make sure that there's space on the stack. And we can see here, there's quite a bit of space on the stack after the stack pointer. So we can feel reasonably confident that we have enough room for shellcode. So we make note of that 396F4338. We write that down, and we're going to go back and we're going to use a utility called pattern offset. So pattern offset is the complement to pattern create. Because pattern create creates the same string every time, and the only thing that changes is the length that you tell it, pattern offset can tell you exactly how far into that string, how many characters it took to get to that point. So we give it pattern create or pattern offset -Q 396F4338, and it tells us the exact match at offset 2006. That means it took 2006 bytes of data in our argument to the trun command before we got to the first byte of the return address. So we're going to need to validate that. We want to make sure that it is 2006 bytes. So we're going to send in 2006 bytes of A's. I'm going to send in 4 bytes of B's and then some number of C's. And if we are correct that 2006 bytes is how many bytes it takes in our input to the trun command before we overwrite the return address will be 42, 42, 42, 42, because that is the hex representation of an ASCII capital B. I should point out at this point, these slides are available on my GitHub as well as these Python scripts. So when you leave, if you want to follow along, you can download Vuln Server. There's links in here, and you can use these Python scripts just to see how it works. And then once you're comfortable, you can walk through the process yourself. I also have links to some learning resources and things like that as well. So I'll put that information on the screen at the end here. So at this point, I have the script that I want to use to see, indeed, can I overwrite the return address with these B's? So I'm going to go ahead and run that. Oh, hey, thank you. All right, so I ran that. The script. There we go. So there's the script. I sent 2006 A's, 4 B's, and some C's. And our script ran. We did not get a response from the server. And if we come down here into immunity, access violation when executing 42, 42, 42, which is exactly what we expected. And if we look in the stack, we see that there is the return address, there is the end of the 2006 bytes, and there is our data that came after the return address, which is going to be where we're going to put our shell code. I want to back up. I forgot to point something out to you. So this is what it looked like when we looked at 396F4338. And since we know that what's in EIP is the hex representation of ASCII characters, 39 is a 9 and 38 is an 8. But we look here, whoa, hey, where are you at? Wow, I just jumped, I don't know how many slides. There we go. So it's the value that in there, if you look on the left, or on the right, it says 8C09. But the value that's in EIP is 396F4338. So it's flipped. Why is it flipped? Endian. We're on a little endian system. So things get pushed onto the stack in reverse byte order, so that's something you'll need to remember when you're putting in your return address. If we were on a mainframe or another big endian system, we'd put things in the order that we expected to see them. Immunity helpfully reverses them for us so we can see it, but it's a little endian system, so the data got pushed onto the stack in reverse. Okay, so we did pattern offset, we verified our offset. So at this point, we know that our stack pointer is pointing to the start of those C's. We know we can reliably overwrite the return address. So if we could put shellcode in the place where those C's start, we could execute it if we had a way to tell the computer, hey, you need to go to this location. And we control the return address. So all we need is a way to tell the computer, hey, go to the location where ESP is pointing and start executing your code there. And in fact, we can do that. There is a command. It's called jump ESP. Jump is like jump from wherever you're at to this next location. And ESP is the location we want it to go to. So if we can find a jump ESP somewhere in the computer, and we know the address of it, and it's in a reliable location, so it's in the same location every time, we can put that address of the jump ESP for our return address. So when we get to the point where the return address gets loaded into EIP, we are telling it, go to where ESP is, which happens to be exactly where our shellcode starts. And that's where we take control of execution. We can't write directly to EIP. And we've talked before that EIP takes addresses. It doesn't take commands. So even if we know the opcode for jump ESP, we can't put that into the return address because it'll look like a memory address at that point, which is not what we need. And we need it to be in the same place every time because we're not at the point where we can bypass controls and figure out where something is living at the time we're running it. We're doing 101 levels, so we need it in a reliable location. So first we need to know what is a jump ESP. And a jump ESP, we use NASM shell. Jump ESP is an assembly language instruction. It says jump to ESP. It's FFE4 is its opcode. So we need to find where is an FFE4, and we're going to use Mona. Mona is a plugin to the immunity debugger. You don't have to use Mona, but it makes your life easier, I find. So I'm going to take a look at that. Okay, so the command, oh, dang it, man. I blame it on having con Ebola from Wild West Hacking Fest. So the command I'm going to run is Mona, and you always preface it with an exclamation point, Mona modules. Now, modules are DLLs. That's what we're talking about. When a program runs, it loads DLLs to provide support for things that it needs to do. Like if you need networking support, you're going to load some network DLLs. If you need graphics support, you're going to load some graphic DLLs. So we run Mona modules. And we see here that we have a number of modules. These are their memory addresses, where they start and where they end. Some other information about them. And then over here are the names. And the names are things that are familiar to us. Things like WS2_32 and kernel32 DLL, user32 DLL. And there are two other ones. We have vuln server itself, the EXE. And we see that we also have ESSfunc.dll. It's in the same path as vuln server, and it happens to be the same version as vuln server. So this DLL is packaged with vuln server, and it gets loaded when vuln server runs. And that's going to be important to us. We don't know how to bypass ASLR. We have to make sure that any module we're going to use doesn't use ASLR. ASLR is address space layout randomization. So what happens when you have ASLR in play is, let's say we find a jump ESP, we find that address in a DLL. If we reboot or we reload the program, the address where that jump ESP lives has now been scrambled. It randomizes it every time. And we're not prepared to deal with that yet. That's an advanced form of exploitation, and we're not there yet. So we need to be able to find a place that we can use every time. Fortunately, none of these are built with ASLR, so we could use any of them. And most of them are system DLLs, and we could actually use them if they contain a jump ESP, but we might not want to. Now, one of the reasons we might not want to use a jump ESP is that's in, say, a system DLL, is because it changes with patch levels and service pack levels. So if you have a service pack 2 system and I have a service pack 3 system, it's very likely that we'll have different addresses for our jump ESPs. That can even change between patch levels, depending on what's getting patched. And it also changes between language pack versions. So if I'm running English and you're running the French version of whatever operating system, we have the exact same patch levels otherwise, very likely that your jump ESP will change. That's not something that makes it so we can't do it. It just means we have to be able to fingerprint our target now and know exactly what it is before we can launch our exploit. That's why if you've ever used Metasploit and it says, like, what's the target? You have to know the target because it needs to do things like change the return address. So we could use anyone, but we know that ESSfunc is bundled with our program. It's the same version. So anywhere we run into version 1 of vuln server, we should be able to use a jump ESP if there's one of those in ESSfunc.dll, and it will work on any computer, regardless of the operating system where it's at. So we're going to search for that. And there is a command, mona find. And then we're going to use -m for the module, which is ESSfunc.dll. So I did mona find. I want to search, and I want to search for this string, FFE4, which is the opcode for jump ESP. I'm going to search in ESSfunc.dll. So we see that we had 9 results here. So there's 9 memory addresses that all contain a jump ESP. All of them are in this area called page execute read, so it's executable memory space, so we should be golden. Now we need to talk about bad characters. So if you remember when I said we send data to the server, and we could send a whole bunch of data, and we have our data, our 2006 bytes of whatever, and then our return address and shellcode. It's just data at that point. And then we hit enter, which sends a carriage return line feed. And it doesn't become anything other than data until if we're able to take control of the return address and then jump to that location where our data is, and all of a sudden that shellcode is now something that's executable, but it's just data. And one of the things we sent in the data was a carriage return line feed, so a hex 0A and a hex 0D, that said this is the end of our input. We also know that strings in C and C++, we talked about this earlier, are null terminated, so the null character, hex 00. that may also tell the server, hey, I'm done sending input. So we need to make sure that nowhere in our data that we're sending contains these bad characters, because that would just truncate our data at that point. So we have to make sure our memory addresses don't contain these bad characters. We know that looking here, none of these contain 0A, 0D, or 00. So we can use any of these memory addresses. That's the next thing you need to keep in mind when you're going through this process, is this concept of bad characters. And there's ways to fuzz for bad characters. We don't have enough time to take a look at that, but in the blog articles that I've provided you at the end of this, they'll walk you through finding bad characters. Some programs will have more bad characters that you can't use than others. And so I'm going to choose 625011AF just because I know that one works. The other ones probably work too. So I have written another Python script here, and I've got my command, and then I've got a bunch of shell script, and I send that stuff to the server. I'm going to walk you through what's happening here. So my command I'm using to generate shellcode is MSF Venom. Because it's 101 level, we're not expecting people to write shellcode from scratch. It's an unreasonable expectation. So I've got MSF Venom. I'm using a Windows platform and x86 architecture. If you were going to pop calc, this is exactly what you would do. This is the payload that we'd use to pop calc.exe. I'm not going to do that, but this is how you would do it. Something called exit func equals thread, which we'll talk about. And then this -e x86 / shikata-ganai. The shikata-ganai is an encoder. It allows you to take your input and then encode it in some fashion so that you have a different kind of output. The reason I'm using shikata-ganai, I'm using an encoder, is because I don't want bad characters. I need to make sure my shellcode doesn't contain bad characters so I don't truncate my input and then I don't have full shellcode getting sent. So I use shikata-ganai with the -b flag for bad characters, and I give it the 3 bad characters I do not want my shellcode to contain. And it generates this amount of shellcode here. And if we were to look at it closely, we'd see that there are no bad characters in there. We have our return address, which is backwards because we're on a little endian system, so 625011AF. So what we're going to send to the server, 2006 A's. Doesn't matter what character we send, as long as it's not a character that is relevant to the system. Like if we sent int, or if we sent hex cc, it's the interrupt code, I believe, which tells the computer to pause execution. We don't want to use that. As long, we can send whatever we want, and it won't matter. And then we put in our return address. I'm going to put in these 8 nops, and I'll tell you why in a little bit. And then I'm going to send my shellcode. And if I'm lucky, if I've done everything correctly, my payload should execute. Hopefully it executes in the foreground, but it's been going in the background lately. There we go. So the reason I chose this rather than popping calc is because honestly, the first time that I ever walked through this process and did exactly what we did here without using a tutorial, I went through and practiced a bunch, and I understood the process. The first time that it actually worked without having to use someone else's code to do it was like magic for me. Like, it was such a powerful feeling that the computer did exactly what I wanted it to. This is a 22-year-old topic. Smashing the Stack for Fun and Profit was published in 1995. And essentially what I have walked you through here has not changed since that point. But there's still people that don't know this stuff. And this is a foundation for learning the next steps if you want to write more advanced exploits. And if nothing else, it's helping you understand exactly what happens when an exploit occurs. I want to point something out. Vuln server is still running down here. It's not paused like it has been before. I can even go close my payload. I can go back and I can run it again. Let's go ahead and run my module, and it works again. And there's a hint to why here. We see that a thread was created, and then a thread terminated exit code 0, so it exited normally. If you remember in our code, I had that exit func equals thread. The default is process. You don't always need to change this, but it happens to be with Vuln server. If you have exit func equals process, it means the exit function for our payload, what should happen with our shellcode. When it exits, it causes Vuln server to crash because it doesn't know how to recover from this error condition. So if we want to be a stealthy attacker, we don't want to crash Vuln server. I used exit func equals thread so Vuln server keeps on running. Just something to keep in mind. The other big thing was, why did I put these 8 NOPs in here? Because this isn't a NOP sled. There's sometimes in buffer overflows, you don't know exactly where the return address is, where something needs to be in the structure, and you can use this thing called an op sled, which you send a bunch of hex 90s, which is a no op. It just tells the computer pass, pass, pass. Don't do anything in this cycle. The reason that I'm using this here is because I'm using an encoder. I'm using Shikata Ganai, which is an encoder. So when it gets to, when it gets to the server, it's not in a format that the computer understands. The processor doesn't know what that is yet. It's like in another language that it doesn't have that support for. So at the beginning of our payload in our shellcode is a stub that encodes or decodes the encoded input. So if we were to just put in our return address and shove our shellcode in there, the shellcode starts exiting like it should. But what it does is it decodes itself over the top of itself. And so it would clobber itself as it's trying to decode, and it wouldn't work properly. These 8 NOPs allow some space on the stack, like just a scratch space. So exactly, so it can shift down a little bit and then start writing above into that space. If you didn't do that, it's not going to work properly. Do you need exactly 8 NOPs? I actually don't know. The first tutorial I ever used said use 8 NOPs, and I've used 8 NOPs ever since. So I don't know if I need more. Just to tell you, like, I am not someone that can reverse engineer programs and write these ROP chains and smash modern day protections. I'm not there on my journey. I just learned this along the way, and I thought it would be terribly useful for other people to learn as well. So I know that this works, and it was mind-blowing for me that it was actually this easy. It was something that I could do with a little bit of practice, that I always thought it literally was magic.gif, and that people that did it were wizards. Now, the people that are doing modern day bypasses, I still feel like they're wizards, but these are the steps they followed, right? Other than maybe Tavis O, who I think came out writing exploits at the age of 1 day. I don't think there are many of us that haven't gone through this learning process to get to this point. So where are we at? We have talked about our shellcode. We talked about how all this works. What do you do after you've mastered vuln server? There is this vulnerable command, and there are another couple of commands that are vulnerable to something called an egg hunter exploit, which is kind of the next step on the journey. But where do you practice more? Where do you practice? How do you find things to practice with? ExploitDB is a great resource. So Minishare has 2 remote buffer overflows in this version. It's an old program. I actually use this exact process that we went through right now to find a buffer overflow and write an exploit for Minishare. I used the exact script that we're using, and the only thing I really had to change was the command, because it's an HTTP-based program, so I think I used get and whatever I needed to speak specifically to Minishare, but I didn't change anything else about the process that we used. And the reason I bring this up is, if you noticed in red here, it says vulnerable app, download vulnerable application. You can go to ExploitDB and search for buffer overflow and see if you can find some of these older, simple stack-based buffer overflows. Find those exploits, download the vulnerable program to your VM, and run it. And you can practice. You can use the exploit that's there to, you can use that exploit just to see, does it indeed work? And then you can go through the process of writing your own exploit and going through the same steps to just get comfortable with this process. Around this same time, there was a bunch of MP3 players that were vulnerable to buffer overflows. If you had these badly formatted M3U playlists, you can use the same process, but instead of now connecting to a socket-based server, you use a script to generate progressively larger playlist files, and then ideally you find some way to orchestrate it so you can restart the program manually and run through all your payloads, because it's a little bit more of a hassle, but it's definitely doable to use that exact same process. The only thing that changes is how you're speaking to the program. I do want to thank some people, Stephen Bradshaw for writing Vuln Server and the blog articles that he wrote that helped me learn. Peter Corland Coder has some great buffer overflow exploits on his some blog articles about buffer overflows, and he also wrote the Mona module, so that is great as well. Our very own Ron Bowes has his Skull Security Wiki that has some useful information in there. His reference material on x86 assembly and the registers was very useful to me. Yeah, there's Ron Bowes. Woo! Also want to thank my friends. Commie Bastard was he was essential in helping me put this together. I was sitting there a few weeks before DerbyCon, and I was ready to quit. I was ready to back out because I felt like I just couldn't do this. That this was, I didn't feel like I knew what I was talking about. And he talked me off the ledge. We sat down and made sure that everything that was in here were the right things people needed to know. And Big Indian Smalls and Jared Bird, also big supporters. They helped me learn a lot in the buffer overflow process. Thanks to the BSides organizers and volunteers for having me out here. Yeah, big round of applause to them for sure. So I mentioned I had some resources for you. So there's links to Vuln Server and Mona.py on here. And I will, if you want to pause, take a picture, but I will show at the end of the link where you can download the slides. So I got some blog articles that you can learn from here. We've got, this first link is Stephen Bradshaw's Beginning Stack-Based Buffer Overflow. And he has a series of blog articles that link from there about how to get progressively more and more advanced doing buffer overflows. Same with Corland Coder Peter. His blogs are there. Another one from Security Sift on writing exploits, as well as some links to learning about buffer overflows and a link to Skull Security. Here's some practice resources because, okay, great, I learned Vuln Server. What do I do next? We use, there's a number of different sites. Exploitexercises.com, I'm told, is good. I have not been to that site, so it should be safe. Over the Wire, the Over the Wire Wargaming Network has some great resources there. Is that the same place as Smash the Stack is? Yeah, so Smashing the Stack, Smash Stack Wargame. There's a lot of these games that you can log in, and they're kind of like terminal-based or web app-based for learning different types of things, including doing buffer overflows. VulnHub, you can download intentionally vulnerable VMs. Some of them are designed more for like network pen testing and web apps, and there are definitely some for learning buffer overflows. Be careful what you download there because we don't know always what people are including in those VMs. And hackthebox.eu. I have not played the games on there. I've logged in. I haven't had a chance to play them, but I'm told that there are some buffer overflow-based challenges there as well as other kinds of pen testing. So with that, I'm Mike at hardwatersecurity.com if you have questions. I'm Hardwater Hacker on Twitter. You can follow me on there if you want. And my slides are available on GitHub. It's github.com/hardwaterhacker. And then it's I want my EIP with underscores. So with that, I want to thank all of you for sticking around. Hopefully I was understandable because, like I said, I'm dealing with con Ebola from last weekend. And I actually went back to my room this afternoon and slept because I felt so horrible. So I'm glad that I could survive. With that, that's all I have for you today. I hope this was useful for you. Do you have any not too painful questions? Yes. So there were two questions. First question was, I was using XP, could you use Windows 7, Windows 10? Actually, you should be able to as long as there's nothing else that is running that's looking for these buffer overflows to be happening, like some kind of protection system, so Windows Defender might block that. But because Vuln Server bundles its own DLL, as long as you're on a 32-bit architecture, things will be the same. If you switch to 64-bit architecture, things will be a little bit different. And I haven't tried it in 64-bit, but it should work. The second part of the question was, I used Python. Could you use another language? Could you use .NET, C#, for instance? Absolutely. You can use whatever you want to develop your exploits in. I'm comfortable with Python. That's what's the easiest one for me to use. But you could use whatever you want and you're comfortable with. Any other questions? Nope, just scratching his head. Okay. All right, well, with that, thank you. That's all I have.